right, so start recording. There's not going to be too much of this. Yeah, I didn't really need to change too much from last year because, honestly, I felt like what we have is pretty good. Classroom. No, it's in teaching because I have a folder for the stuff that's public and the stuff that's private. So, exam to practice. Right. Okay. Right. No panic. Good idea there. So, and I'll tell you what maps to what for each page of this exam. Yeah. You have a question?
Like the previous exam, we put together a page with
Yeah.
different methods of maps.
I think I have some of them. Now you're making me think. Did I put that on the exam? Yeah, there's some. Yeah, there's some there. So there's string methods, tree methods, and map methods, right, that I have listed on the actual exam. So they don't really go into much detail. I just remember, I've just give you a kick to jog your memory if for some reason you don't have it on your cheat sheet. By the way, you should have a cheat sheet for this exam.
So we can still use like he said and stuff that's not on there.
Yeah. Yep. I mean, yeah. But I mean, you'll see that there's that add and remove.
You are? What's that?
Add and remove don't really come up too much in the terms of writing something for trees. All right, so this first page is very representative of what the page is going to be on the actual exam. So on the actual exam, there will be a page like this. Okay, you've got where basically here's a scenario, choose the data structures. There will also be a problem like this on the final exam, where basically here's 4 scenarios, please give me the appropriate data structure, right? You know, part of learning data structures is to not just learn how to use them, but when to use them, right? So you need a model which patient should be seen at a hospital. Patients should be seen in as close an order of arrival, but patients in a more severe situation should be seen first. So which of the, so what data structure models this?
The British version of a line. Is it queue?
Yeah, that's a queue, but it's not just a queue. It's a priority queue. Because people who are more...
Oh, they're triage.
Right, because they got a triage. So the reason you wait in hospitals in the ER is because of triage, right? A baby with a fever above like 100.6. They win. And by baby I mean less than 6 months.
Yeah.
Right? You with your head injury, if you're still talking conscious, you might be seen after that. Broken arm, sorry, you're on the back of the queue. Maybe we'll give you some Tylenol to manage the pain or something like that. But you'll be seen. But basically, it's all about like, is this potentially lethal? If we don't solve this right now, is it potentially lethal if we don't solve it in a couple hours? And does it suck? Those are basically severely injured, moderately injured, and lightly injured right there. So priority queue, right? People who've been waiting the longest should be seen first. But if obviously there's a more severe consideration, right, then we want to make sure all the severely injured people are seen first before the moderately injured, right? In battlefield situations, this gets really, really nasty. Like, we can't save him, but we can save these people, right? So that's a priority queue, and it's but it's a very good scenario. But it's a very good situation that simulates, or a very good fit for simulating a priority queue. All right, router needs to hold packets in a buffer and deal with them in the order they appear. That is a regular queue, right? Buffers are basically one of the big uses of queues, right? Where we get in information, and information is coming in, and we need to process it, right? We want to process it in order. Comes into the queue, it gets processed. Okay. This one, you need to model a hierarchy. Or an org chart or something like that. What data structure is that? That is a tree. Anything that's hierarchical is kind of a natural fit for a tree. Notice that tree encompasses basically stuff like family trees, as well as the data structure we actually care about, which is binary search trees, right? We care about binary search trees because we can turn any other tree into a binary search tree with a bit of manipulation, or most of them into those. And finally, you need a data structure to hold your previous decisions in case you need to backtrack. So what data structure do we use for backtracking? The stack, right? So if you have to unwind something or go backwards or process stuff from the most recent to the least recent, then it's a stack. Okay? So this page is not going to be similar to what's on the exam. What will be similar to what's on the exam is the quiz you took on tree definition and stuff, like where you had to fill in the blank. That is much closer to what you'll be doing. Okay? So that quiz is much closer to what you're going to be doing, but this is still a good review. The node at the top of the tree is called a what? Root. Please don't tell me the node at the top of the tree.
Grandpa.
I know. The links to a successor, the links from a successor to from a node to its successors are called what? Branches. I will also accept links or edges. Oh, that one's fair. There's root really has only one correct word. Links, branches, edges. There's a lot of correct words. The predecessor of a node in a tree is called a what? Your parent. And the node 2 above you, that would be your grandparent. And if we generalize that out, what is that generalized relationship? Ancestor, right? Remember family trees.
I thought the root, like all of them were self-contained. So is root also a correct answer?
The predecessor of a tree. No, that would be your parent. The predecessor is your parent. Your predecessor would also be a root, but it's your parent. It's the root of that parent subtree. Right. Nodes, if you have the same parent, you're what? Siblings. All right. So describe without using code how to calculate the height of a tree recursively. So here, what is height? Height is basically the number of levels that the tree has. And the way you calculate that recursively, right? For us, it's fairly easy. You just find the longest strand and count down. But for here, what you have to do is, when you think about it recursively, it's always thinking about it in terms of a local decision, right? How do I, just from here, with me and my 2 children, figure out? So first thing I have to ask myself is, am I null? If I'm null, that's easy. My height is 0, base case. Otherwise, what's my height? Well, I don't know my height. Figuring that out is hard. So I'm going to ask my left child and my right child to figure out their heights. And if I ask them to figure out their heights, then I could take the bigger one of them and add 1 to it. And that's my height, right? So if my left subchild is a subtree of height 3 and my right subchild is a tree of height 1, then I'll say that my height is 4 because my left subtree is bigger, and I'll take that and add 1 to it to account for me being on top of the tree of 3, right? And of course this is recursive, but now you can actually as one nice thing you do have in Java is the is the math.max method, if I recall correctly. JShell. Math.max. Right, given 2 arguments, give me the bigger of those. Right, so you can say, okay, if my give me the bigger of the left subtree or the right subtree, or the height of my left subtree or the right subtree. So math.max is that is very convenient because it takes out an entire if statement that kind of tedious, which is give me the bigger one of it. Of course, since there's a math.max, there's also a math.min, assuming I do it without hitting a random character in there, which gives you the smaller of the two. But math.max, it's not necessary, but if you remember it's there, it might shorten what you have to write. Okay. So for this one, I have a caveat because some people are like me are jerks. Draw an example of each of the following types of binary search of each of the type of following binary trees. Draw a different example for each possible tree, full, complete, and perfect. And the reason I come up with a different example for each of those is because technically you could just draw this for each one of them and say I'm done. Because that is both a full, because one node by itself is just full, complete, and perfect. So what does the full definition mean? What is the definition of a full tree? Yes?
It means every node on the tree has either 0 or 2 children.
Right. Every node basically is a bachelor and living by himself, or has 2 children and is very, very busy. Right? So no middle ground there. It is a kind of a recursive property in the sense that you're only full if your children. It's only possible for you to be full if both your children are full. And as you saw on the exam, on the practice exam, it is possible to program this recursively. Complete, not really so much. You can't program a complete tree so much. But let's go and skip to perfect because perfect is fairly straightforward. Basically, it's a tree of height h, and basically every single position is filled in that tree. So mathematically, that means that if you've got a height of 3, then the number of nodes you're going to have is 2 to the third minus 1, or 7 nodes. And there's only one way to draw that for a binary search tree. Which if I come through here for a binary search tree, right? Of height. This is a perfect tree of height 1. Perfect tree of height 2. Perfect tree of height 3. Right?
It's perfect and full.
Yep. Perfect trees are full. Perfect trees are always full because every node on the bottom is going to have no children, and every node that's not a leaf is going to have 2 children. It's just so a complete tree is a bit trickier. It's one of those I more know it when I see it kind of stuff. Which is that basically that we're filled left to, is that the tree is perfect on the topmost layers, but the bottom layer where the leaves live, and only the leaves live here, it's filled from left to right without any gaps. And these are used for heaps and stuff. So this is a complete tree. This is a complete tree. If I remove this second node over this node over here, this right child, it's going to no longer be a complete tree. All right. Complete. I will not ask you on the exam to write a program that detects whether a tree is a complete tree or not, because I'm not even sure how I would do that. So, actually, now that I think about it, you have to do the easiest way to do that is a breadth first search kind of deal. And as soon as you find that basically that there's like, it's actually tricky. It's annoying. But anyway, this complete tree is more knowing how to draw them, right? I'll probably ask you, okay, here's a tree, now add nodes or remove nodes from it to make it complete. Right? Yeah. So I will ask you, this page on the actual exam will be combined with this page, basically asking you, hey, here's a tree, make adjustments to the tree that I've already given you to make it full or perfect. Or if you remove these nodes, removing what nodes will make this tree perfect? Yes?
You say we have to use a different tree for each example. Would we be allowed to just draw a full tree with unique heights for each one to answer each problem?
I suppose you could. All right. this question is going to be exactly the same as it is on the actual exam, except the numbers are going to be different, but you get what I mean. So, it's, if you mess up on this one, like make a minor mistake, totally possible, by the way, where you just like totally miss a number, right? And that utterly changes the structure of a tree, right? Or if you just forget, like, or if you just like, you know, you put one down and then, you know, you read 17 and you put down 11, right? Something like that. Because, or rather, you put down 17 and your 17 looks more like an 11, so when you're going through it again, you read the 17 as an 11, and it kind of messes up everything, and you don't really think about it too much. That's like a point off. So, you know, it's where basically you have, where, you know, that picture of the dog where on the computer where he's saying, I have no idea what I'm doing. Right, that's where how you get his ear on this one. So. Unless you actually draw that, in which case I'll be very impressed and very confused. So, all right, so draw the binary. So what you do is, right, we just simply assume we're building a binary search tree from scratch, right? We put 42 on top as the root, and right, the idea here is that we're adding these in order. 42, then 10. 10 is less than 42, then 50, then 12. Right, and these, and I literally just kind of just make numbers up for the exams. So the trees get really, you know, unbalanced looking, so don't worry if it's not artistic, you know, aesthetically pleasing, you know, don't worry about that so much. 80, right, this one, negative 12, remember negative 12 is less than everything. Yeah. Okay, that can throw you. Again, that's just a point. I understand that sometimes the negatives during an exam, you can just kind of blank on the negative. Perfectly understandable. It's not like, oh, the student somehow got to college without knowing what negative numbers are. Yeah. Like, no, I'm like, that's an easy one.
That's a lot for real.
so 96 goes all the way down, it's less than 100, so it goes here, right? Where I start kind of questioning your abilities is where if you put the 96 over here, right? Yeah. That's where we kind of get the question. So, 90, but fortunately, well, even more so if you did 96 over here and then 105 over here, then I'd be really questioning it because, you know, so 96 goes here, 105 goes here, and then 86.
So just be consistent with your mistakes.
Yeah, exactly.
Yes.
It's a feature. 86. So 86 is greater than 80, less than these guys, less than this guy. 86 goes over here. And 72. 72, again, greater than 50, less than 82. 72 goes over here. Okay? On the actual exam, I'll give you one to, what I have you do is I give you one to draw, and then for the delete one, I'll give you a tree rather than having you work off the tree I made or you make. Because honestly, it's just on the practice exam, it's easier for me to say, make the tree and then delete it so I don't have to write up a new tree. All right, so remove is a bit trickier, but again, what I'm going to do for the remove method on the tree is that I will give you a tree. And I will tell you, remove, you know, here's the tree, show me what happens when you remove this item, then this item, then this item, right? So 3 items, just like we were adding multiple items to the tree, you're removing multiple items to the tree. Now, you can get away with just putting in the final answer if you somehow manage to magically work it all out in your head. I do not recommend this, especially because if your final answer is wrong, you're not going to get any credit. Yes?
On that question, you meant in order? Remove the following.
Yeah, remove 42, then remove.
Okay.
So
if I saw that, I would not have done 42 first. I would have rearranged it.
Okay, yeah. So 42, then 12, then 17, then 96. So what you have to do here is, but again, really, so if you want to be sure about it, like if you want partial credit, just kind of show me this is what happens when you remove the first one, then the second one, then the third one, right? Okay, so 42 is our most difficult position here because removing 42 is removing the case where we have a node and has 2 children. So to remove it, we go all the way we go one to the left and all the way to the right. We find the next in order predecessor. It's also a valid choice to find the next in order successor, 50 in this case. All I care about is consistency, right? So if you go within the next order, if you go left, then all the way to the right, then do that for all your choices. Don't do left and right, and then for the next number, go right then left, right? I'm going to go left and right because that's, I don't know, that seems to be a standard. So go to left all the way to the right. 17 is the next in order predecessor, meaning it can replace 42. 17 goes up here, delete the old 17. Next number to delete is the 12. 12, yeah, has no children. Super easy. You just gotta go bye-bye. Okay. 17.
We just did.
I know. This is like it was intentional or something. Okay, 17. 17, go one to the left, all the way to the right. It's like this was specifically designed as an example for like that weird edge case. Where you, right, well you go left, then you go all the way to the right. There is no right, you're all the way to the right. That 10, as it turns out, is the next in order predecessor. So that means you take this guy, replace it with 10, delete the original 10, which means we're deleting a guy with 1 child. That means we have the parent adopt the child. Nice thing about papers that or whiteboards that becomes super easy. And then delete 96. Again, 96 to delete a node with 1 child, all you have to do is go, yep. You just simply have the parent adopt the child. Parent of the guy you're deleting adopt the child of the guy you're deleting, right? Okay. Right. It's just so when you remember. So when you're doing this, just remember when you're doing deletion, there's 3 cases. There's 1 child. Sorry, if there's no children, just simply erase it. If there's 1 child, you have the parent adopt the child, right? You have the grandparent adopt the child, might be a better way to put it. And then if you have 2 children, find the next in order predecessor, copy it over to what you're deleting, then delete that original number, that number you just copied over, at its original position. That will reduce to the case of having 1 child or no children by default. So it reduces that to a simpler case. Okay. Next, this will actually be the pre-order post-order kind of thing. That's going to be attached to the tree question. Well, sorry, to the tree adding question, where I'll ask you to do, hey, here's the tree. Like here's the tree you just wrote, and then I'll ask about pre-order or post-order questions with regards to that. So remember, pre-order is. That's in order. In order is left, middle. So for a pre-order traversal, that means handle my children before I handle myself. So left, right, and myself. For post-order, that means handle everything, handle myself. Oh, sorry. Wait, no. Back that up. Pre-order is myself, then my left and my right child. Right. Pre-order is being greedy. I'm going to handle myself before I handle my children. Post-order means I handle myself after I handle my children. Right? Pre-order is the flight mask comes down, you put it on yourself first. And you do that, by the way, because lack of oxygen kicks in really quickly. From what I hear, not had personal experience with that. Okay, so draw the Min-Heap. So this is a question that gets also asked. Again, this is one of those same question, but we just change the numbers up. I suppose actually I should probably adjust this because you're not going to be able to see it from this tiny screen. I just realized. So give me 1 second to add scene 2, add video capture device, add existing. There we go. Okay. So we are going to be drawing a Min-Heap that I and same thing on the exam. I'm just going to give you a min-heap, and you want to draw what happens as you insert these items. Okay, that's what we're going to do on this. This is where, so students don't typically mess up on the adding tree, but if they're going to mess up somewhere and still do well on everything else on the exam, it's on this page for some reason, right? Because the adding rules are different. Remember, at every point, you have to have a complete tree at every point during the addition. That's kind of the rule there. So first thing we do is add 8, right? It's at the top of the heap. Now remember, the rule for min-heaps is that basically the heavier items sink and the lighter items rise to the top. Okay? Next thing we add is 10. We add it, and we just always add kind of to the top, right? Yep. 10 sinks down, and 10 sinks down. Actually, I'm sorry, we don't add it to the top. We add everything to the bottom of the heap, right? And heaps work on the bottom. So like when we add, for instance, 50, we just add it right over here. Next thing, we add 20. 20 and 10, that's perfectly fine. Right, we add 8 to the bottom, then we add 10, then we add 50, now we add 20. Right, it's all at every point you're adding a node such that the resulting tree will be complete. Next we add 1. 1 is super light. So it now will bubble to the top where the heavier item is sinking down. Right, so 1 and 10, swap. 1 and 8, swap. So remember, we don't add to the top, we add to the bottom in a heap. So now we add 4. 4 swaps with 50. 50 sinks down, 4 bubbles up. 4 compared to 1, 4 is just going to stay put because it's heavier than 1. And then 3 is the next one. 3 was lighter, so it bubbles up to 4. So it bubbles up and swaps with 4. Yeah, and that's it. That's what we've got. So we've got so at every point, right, we want to end up with a complete tree.
It doesn't care that 8 and 3 doesn't care that there's no left to right order.
Right, we don't care about left to right order. All that we care is that it follows the heap property, which is that the top of the heap is the smallest item, and that every sub-heap follows that property. It's also a recursive data structure. Right? 3 is the smallest item in its sub-heap. 8 is the smallest item in its sub-heap. Adding to a heap is log n. Removing from a heap is log n because the most items you're ever going to be swapping is the height of the tree, which is log n. Or log of the heap. Right? Heaps are just these special kinds of trees. So, using the heap you just drew, remove an element. Show what happens to the heap after removing an element twice. The only valid place to remove from a heap? Yes.
Removing 2 elements, not
Right.
1 element twice. So
Yes.
it'd be like removing 8.
We perform the remove operation, right?
Yeah.
We can only remove from the top. So we're going to remove, and then we're going to remove. So, and you know, these operations are also atomic, so meaning you can only do one at a time. You can't add and remove simultaneously. You do an add, and then you do a remove. So to remove an item, what we do is that we kind of just copy the item out if we need it, and then what we do is we take the item in the last position in it and move it to the top. Again, at all points, this tree is complete. So now we basically follow the same rules, but from the top going down. So the lighter items sink. Sorry, the heavier items sink and the lighter items rise to the top. Right? 4 is lighter than 8, so it doesn't swap with 8. But 4 is lighter than 3. Sorry, 4 is heavier than 3, so it sinks down. And so now we just continue following 4 on its way to the bottom. Right? And on its way to the bottom, we hit 50. 50 is heavier than 4, so 4 ain't going to move.
So you have to do it twice, or would it be complete?
Oh, it's still complete right now.
Or
You do it twice, but now when we do it twice, so now we're going to remove 3. We're going to move 50 up. And I like this example because with this one, right, this thing's heavier than both its children. So what does it switch with? And the answer is that if you're going to switch with your two children, you're always going to switch with the smaller one, which is 4. And the reason for that is that when you switch with the smaller one will rise to the top, and it will be the minimum of that heap. Right? If we moved 8 would have been bigger than 4, and that would have made the heap. 50 doesn't sink any farther because it's hit bedrock. There's nowhere further for it to sink. Okay. This page is, again, exactly like you would see on the actual exam. Just numbers different. There's a lot of questions. I like this one. I like this exam because there's just a lot of questions where I can say it's the same, but we just changed we just changed a couple of the numbers. Huffman coding. Okay. Not only will you have this on this exam, you'll have a question like this on the final exam. So be sure to get it right both times, is what I'm saying. Especially the second time around. Because it's worth a full 10 points on the final exam. Okay, the biggest issue is that students forget that basically when we put stuff back in to the priority queue for Huffman coding, it's a priority queue, so it reorders. Right, so what we need to do is figure out what these guys are. Okay, and let me probably show the problem on the recording in case you're watching this and are completely lost. So, boop. There it is. Pause it if you need it. And then here's the second part, which is to encode Apple. Okay, now let's go back to hopefully you can see, I doubt you can actually see anything. I don't know. You can probably make it out, maybe, who knows. No idea. No idea at this point. So, all right, consider the document that has the following symbols. The room isn't great for whiteboard stuff. I'm trying to do it not on a whiteboard. It's like takes super long and it's messy. So here's the symbols and the frequencies. X is the smallest. 1. Then L.
Yep.
20.
And P.
Then P with 40.
Alpha with 50. Right. And then echo is 60.
Okay.
Shut up.
XLPAE. Lixpay. Fine. All right. So what we do? So it's always the same operation. Pop off the top two. DQ the first two nodes. Combine them. Reinsert. So X and L get DQ'd. The first thing that gets DQ'd goes to the left. The second thing that gets DQ'd goes to the right. And they get combined into a new node. And they basically become the left child and right child of a new node with at the center that has a combined weight of 21. So XL gets reinserted back in, right? Combined weight of 21, and now we reorder this queue, which means that this guy goes to the beginning because it's smaller than everything else. Okay? Next, XL and P. XL gets DQ'd, P gets DQ'd. You get XL on the left. So this node goes on the left. P goes on the right. So that was 21 and 40, which gives us 61, right? 61 goes over here, which is XLP, I'll just put it down as. And now we do A and E. A gets DQ'd, E gets DQ'd. Let's see, yep, we'll put them over here. A, E, goes on left and right. Combined weight of A and E, that was what? 40 and 50, sorry, no, it was 50 and 60. So it gets a combined weight of 110. So A and E gets put into the queue. at combined weight of 110. DQ both the things. The last two things I'm not even going to bother with figuring out what the weight is. Well, it's 171. Couldn't help it. 171, they DQ, you put them into a thing with a combined weight of 171, right? Why does it go in this order? Because the thing that gets DQ'd first gets on the left of the new thing that gets DQ'd second gets on the right of the new node. And then you reinsert that into the priority queue, but by that point you're done. You've got the entirety of the tree at that point. Now for some things there's more than one way to do it. For this, there's not. Now I like this question actually because it's very easy for me to grade because I just have to see, oh, do they have the right structure? Do they have the right encoding/decoding? That's right. So I might ask you to encode something or decode something. Typically I ask you to decode on the exam because if it comes out gibberish, then you know that you did the Huffman tree wrong. So regardless, if for encoding and decoding, that part is independent of the tree. If you did your Huffman encoding wrong, like if you built the tree wrong, but you use that for your answer, well, for this part, I'll work off of your answer, right? So I think the weights are different on the exam. It's like 7 points and 3 points. So a lot of times, if you get this completely wrong, but you get this right, it'll be 3 points, right? Because I think on the exam, I've weighted 7.3 as opposed to 6.4. So to encode apple, we have 0, 0, 0, 1, 1, 1, 0, 1, right? So left branches are zeros, right branches are ones. To figure out what apple is, here's the A. To get to A, you have to go 1, 0. So we put down 1, 0 for A. Then we have two P's. A P is 0, 1. So 0, 1, 0, 1. And then LE would be 0, 0, 1. 0, 0, 1. And then E is 1, 1. So suppose I told you on the exam to decode this string instead. What you would do is you'd start at the root and you'd go 1, 0. Oh, I've hit an A, so the 1, 0 is an A. Then you'd start at the root again, but this time from 0, 1 because you've already got 1, 0. Now you go 0, 1. Oh, 0, 1's a P. Here's another 0, 1. That's also a P. Then you go, okay, 0, 0, 1, that gets me to an L. And then 1, 1, that gets me to an E. Okay, and then you're like, the answer's apple. Yay. All right. Okay. Now the part you've all been waiting for, the coding part, right? Coding part will be recursive tree solving problems. So I'll go through all the methods, including the practice ones. Here I will just need to create and let me go and push this back. Here what I need to do is just create a node class for this. Private static node, private static class node E item node E, and then I'm just simply creating this so that it will compile correctly. Node E right. That's really all we need. And then we need, we need a public node E. So public node E item, take that in, this dot item equals item. There we go. So here, first question is size, which says, write a method given a root or of a tree or subtree, computes and returns the number of nodes within that tree or subtree. You can't use the side method. Forget it even existed, right? which I thought was a nice restriction there because otherwise it would be kind of trivial. So here we need to count each of the nodes in the tree, figure out what the size of the tree is. Okay, there we go. Let's go ahead and quash the compilation error by saying, hey, return -1 for right now, just simply to quash the compilation error. So how do I do this? Well, let's always start from our classic base case. What if the root is nothing? The root is equal to nothing. If the root equals null, what is the size of the tree then?
0.
Yep. So return 0. Also, apparently, I don't have my fonts. I'm a stickler. Fear code. Enable font ligatures. There we go. There we go. So return 0. If I don't exist, then the height of this tree or subtree is 0. Okay. Otherwise, then what I've got to do is I've got to figure out, okay, how big is this tree? Well, let's think about this. I have myself, which is 1. I know I'm a node, so the size, so we're at least size 1. And then I have this left child and the right child. I have a left subtree and a right subtree, and God knows how big they are. I don't know. They don't call me.
Wait, are you sure?
Int left is equal to size tree root dot left. I'm just simply going to ask the left side of my tree for how big it is using this method that I'm currently writing. And then I'll go ahead and do the same for my right subtree. Size int right. So I get the left, I get the right, the size of my left subtree, the size of my right subtree, and then I say, hey, there's my left, my total height is however big my left side is, plus 1, plus however big my right side is. It's actually all you need. Right? If I don't exist, then the size of this subtree is 0. Otherwise, I exist, so that's 1. And then I got to figure out what the left subtree is and the right subtree is. And we have a method to do that, which we're currently writing. And if they don't exist, they'll just simply return 0. Okay, right? Cursive methods are nice and easy like that. This one's slightly trickier, slightly different, because we have to consider more cases. So it says, write a method which, given a tree, returns whether the tree is a full tree. Now this is slightly different because we have to consider 4 possibilities as opposed to, or we have to consider 3 base cases as opposed to 1 base case. But fortunately those are fairly easy and straightforward base cases, right? Base case number 1. Well, a couple base cases actually. So first off, if tree equals null. I don't know why I said tree rather than root over here. Whatever. If this tree is null, if this tree or subtree is null, I don't know what I'm going to do. I'm just going to return. I'll go ahead and return true, I guess. Sure, I don't know. We'll figure that out later. Okay? That's perfectly fine to just put that, but right, we want to just react for the what if we're null. Right, I suppose if the tree is empty, then it's technically full because all the nodes have 0 or 2 children.
There can be a tree. You can't get assign an attribute to a tree that doesn't exist.
A what?
How can you assign an attribute to something that doesn't exist? That's like saying, oh, the magic dragon is purple.
I mean, but he's green. Everybody knows that.
It's not real. You can make it whatever you want.
Well, I made him green. All right, so there. So there's a couple base cases though, which is that if my child, here I actually have to care about and actually directly inspect my children, which is that, hey, if tree.left is null and tree.right is null, right? If I don't have any children, then I know I'm a full tree. So I'll just return true. Else if, which could just as easily be an if, but I like to make these else ifs. If I have one child, else if tree.left, if tree.left is not equal to null. So in other words, if something exists on my left side, but something doesn't exist on my right side, then that means I've got one child. So return false. Else if the other, and then on an exam, it's perfectly acceptable to write
Reverse of above.
Yeah.
Inverse.
Yeah, reverse or inverse of above, right? It's perfectly or you could just simply say else if swap left and right, right? And I'd get the idea because it's very symmetrical. So if you're feeling sufficiently lazy and brave, you can do that. Trust me, I am a very understanding grader when it comes to this kind of thing. So if we don't have anything on our left, but we have something on our right, return false as well. Else, that means we have two kids. But we can't just return true because we haven't checked if they're full or not. In this case, actually, it's not too bad because all we have to do is return is full left, or tree.left. So ask if my left tree is so I'm only going to be full and only want to return that true if my children are full as well, right? It's a recursive property. It's only a full tree if my children are also full. And as far as this, I mean, technically I guess we don't need this except for like the topmost root. You don't want it? Because it's only gonna, I mean, if you put true or false there, it's not gonna really matter. So, let's see. I also had a similar question to this, which was equals, because this one is way harder. This one is fair game for the exam. This is about the difficulty of one of the questions, and I think these two questions are representative of the difficulty. Like, you will have two tree coding. Technically, it's one tree coding question, but I split it into two. Okay. For this first one, it's going to be fairly easy. In fact, I will give you a hint. I've already gone over the answer for that today, as the one you're going to get on the practice exam, on the actual exam. For the second part, there will be a bolded sentence. A lot of students forget that part to handle the part in bold, and that's a 3-point mistake. But it's like a single line, so it's not too and if you miss that but get everything else right, it's perfectly fine. You just miss 3 points because I find it a significant part of the problem. But anyway, this is representative of that difficulty. And this extra practice here is a step above, so we're going to go ahead and do that. Okay? And it's mainly a step above because it's annoying as all to write it. Right? It is essentially the same thing as what we've already done, which is the equals method. Now here also, I just was trying to be very, very clear that that it's not that just that they don't have the same contents, but also that they're the exact same, presented the exact same way. Right? Basically, do they have the same, how to say, that they basically have the same structure, yeah. Pokesec, Boolean, no worries. We're just wondering why, oh, right, forgot to put this part in, the E, bleh. All right, so we've got a tree A and tree B. So how can we tell if they're equal? First,
If they're both null.
yeah, so if they're both null, if tree A
You at least get that.
is equal null and tree B is null, guess what? They're equal, right? Makes sense, so return true. Right, if they're both null, congratulations, they're both equal, so we're going to return true. Hopefully that makes sense to everybody so far. Right? Otherwise, again, other base cases. Else if, and again, we'll just copy. If A is present but B isn't, well then if one's null but the other isn't,
Yeah, no.
it's return false. They're not equal. Else if, and again, this is why I say you can use some shorthand when writing this, right? Right. Especially when it's repetitive like this. Otherwise, if tree A is null, but tree B, if we have tree B but we don't have an A, right? It's also false, right? You've got something, you've got nothing, not equal, right? It's like an entire political ideology or something like that. Yeah, praxis via computer science. Yeah. So, the else tree A, tree B. Otherwise, they both have stuff, and so we now actually have to bother checking the contents of the tree. So first off, I guess check if the items are equal. So if tree A dot item dot equals tree B dot item, so check if their items are equal. If they're not, return false, right? Because the contents of these guys aren't the same. Return false. Otherwise, they're the same, so now we have to check their children, which is simply put return. Okay, well, we need to check if our left subtrees are equal and our right subtrees are equal now. So now we say equals tree A dot left tree B dot left, right? Our left subtree is equal, and our right subtree is equal.
No, right. You're right.
Yep, right. Ah, that was exciting. Clipboard versus editor. I don't know what's going on there. Discover new. That's how I discover like half this keyboard shortcuts is from me sloppily typing and like, how did I do that? Let's try it again. That's exactly what happens. So, and that's this. So it's a bit of a mess. It's not. It's a bit of a mess logically because there's a lot to work through, especially if you haven't done this problem before. But the more of these you do, the more comfortable you can be with these. All right, maps. Right. So again, just accounting. Actually, in about 20 minutes, they're gonna my students in. Sorry, at 2 o'clock, my students in 1051 are going to be using a dictionary to solve a problem in Python, hopefully, if they're smart. I mean, they don't have to. They can just use 4 variables instead, but I mean, it's just a matter of doing what I showed them how to do, I guess. But anyway, so remember, there's basically 3 ways you can use maps. You've got your key value retrieval, which is kind of like if you're making a database or something, right? You've got your categorization, which was the hangman problem. And then you've got your counting, which is the most common thing. And let me tell you, that is super useful when you're doing like programming interviews and stuff. Like you'd be surprised. The map. Using maps for counting or using them for categorization. Super, super useful. In fact, there was a kind of a small panic among companies, like we need to find problems where this isn't, where the map isn't the cheat code.
Oh, yeah.
So here, this is a classic thing, either doing letter count or word count. Here we're saying, here's a string. Yeah, I'm just basically going to have you, on the exam, I'm going to have you, here's a thing, iterate through it, count the occurrences of things within this thing, right? Not something you could do with an array very easily is kind of the point. Okay, so here I want to look at for each character and how often that character appears. So, yep, given a string. I thought I copied it. So public static map character copy. Here we go. Import map, import class. Return counts. What is counts? Counts will be what we're making. It is going to be a map, character to integer. I tell you the generics right there. Counts, right? We're gonna have a character. This is the character. This is how many times that character occurs in the string. New hash map. 1 point penalty if you instead do this, right? Because you got to remember that's an interface, right? What kind of what map is it? Hash map, or is it a tree map, right? Either of those work. You can use a tree map, sure, but we're going to do a hash map. Remember, difference between a hash map and a tree map is that hash maps run in constant time for all their operations, but they sacrifice any order. Tree maps use a binary search tree, which means that they can keep stuff in order, because trees run on order, but all the operations are in log n time, which is still really freaking good. So, anyway, I like to do this kind of for loop when we're going through letter by letter in a string, which is for character letter in word. Now you can't iterate over for it like that because string doesn't have an iterator. But what we can do is just turn it into a character array, 2-char array. Right? If you put down 2 array, then you're going to instantly fail the exam and kick you out of the class. No, I'm kidding. I'm not going to care. I'm not going to care if you put down 2 array or versus 2 character array, right? I try to treat these as close to like whiteboard interview questions as you can, and try to grade them like I would on a whiteboard interview, right? Which is basically minor syntactical things where you're making yourself understood, right? Right. In 1058 and 1068 and 1051. We really cared about the syntax and, that it's called a double, not a double, right? Okay. I've never actually seen a student do that, but do you understand? Like, let's just say that if you really don't understand in 1051 or 1068, it's very obvious you don't understand. So there's really not too much of a distinction between bad function calls like 2 array versus 2 character array and complete gibberish. But now we're here and you guys can program. I've seen it, right? So believe it. So if you do this, just if it seems to make sense, even if you're using weird fake things like lambdas, totally fake, doesn't exist.
Yeah, lambda functions don't exist.
Yeah, totally.
Around for 1,000 years.
my pH so let me just show you this because I want to establish some kind of street cred. Math PhD genealogy.
I think that 1,000 years back.
Yeah.
I'll say 100.
Okay, so Andrew Rosen. Okay, so I'm on here. I should be on here because I registered on here. Right, here we go. Georgia State University 2016. there's my dissertation, there's my advisor, there's their advisor, and there's their advisor, and then there's their advisor, and their advisor, and their advisor is Alonzo Church, which, right, so I've got Alonzo Church, who did lambda calculus. So he's best known for the lambda calculus and the Church-Turing thesis, which is basically the entire thing basically we're saying what are things that can be computed, you know. So it's kind of what's the halting problem? Giving here's a program in a computer. Does it ever stop? Does it ever work? Can this computation model solve this computer? Right? Here's given a computer, give it another computer and a program, and ask if it runs forever now. So there's also some math problems that you just really can't solve, but it's okay. But he did lambda calculus. But anyway, it sounds that's less impressive than it actually seems to be frank, because notice how many students he had. Right, so that's a pretty huge family tree. And if you keep clicking up this, you eventually get to guys who, you know, Poisson. You eventually everybody gets those as their advisors eventually. They're at the top.
That's not fair, right?
Like
Mr. Algebra.
Yeah, it's like everybody. Yeah, we show a link to Euler because not that he was ever given a PhD, but you know. Yeah, advisor Euler, and Euler was Bernoulli.
This is so much fun.
Right, so basically, there is this kind of genealogy project. I don't know. What, Bernoulli?
Yeah.
Oh, it's a different Bernoulli. Yeah, they were like a math family, so. All right, so point being is that basically, the other thing that we talk about also is that there's the whatchamacallit. There's the Bacon number and the Erdos number. Erdos number being the collaborative distance between mathematician Paul Erdos and another person, right? So if you wrote a paper with Paul Erdos, your Erdos number is 1. If you wrote with somebody who wrote with Paul Erdos, your number is 2, and so on and so forth. My Erdos number is 5 because my advisor's Erdos number was 4, and I published a paper with my advisor. Why does this exist? Because nerds. That's why. Because he published. He published 1,525 math with over 500 people. So he was very influential. Anyway, back to this. Okay, so we've got our counts. We're going to iterate through every letter in the string. Okay, and then our basic strategy for whenever we're dealing with counting characters like this is, hey, have I seen this letter before? So if not counts dot contains key letter. So in other words, if I've not seen this letter before, this is the first time I've seen it. So I've seen it a grand total of how many times? Once. So counts.put letter 1. Otherwise, I've seen it before. So counts.put letter, the number of times I've previously seen it, counts.get letter, and then add 1 to it. You can't just go plus plus, unfortunately. Wish you could. That would be so much easier, but you can't. Because you wouldn't be modifying the thing in there. You'd be... Okay? That's all you have to do. This should be... If you're comfortable with doing this over kind of any kind of data structure, you'll be fine. Okay. I'll come back to this in a bit. analysis. What are hash collisions and hash tables? Why do they occur and how are they handled? So, they occur because collisions in hash tables occur because you don't have infinite space. So, two things will often get hashed to the same index, and they'll try to occupy the same index in the hash table. That's what a collision is. Two keys try to occupy the same index. Okay? They occur because space is limited in the hash table. And while we have a lot of unique keys, we don't have unique indices to hold the key.
Is that different than a hash collision? Where
This is a hash collision.
Okay. I always thought of it as like you have two files.
So
this one's modified, but they can create the same.
Yes,
like
that is a collision. You are literally looking for that kind of security exploit. You're looking for the changes you can make to a file so that your security hash, like MD5 or SHA, will end up with the same key because the universe of keys they generate is huge, but it is limited.
Okay, I can think it's the same.
So now you can blame this is one of the things we can blame Bitcoin for because people make ASICs, these special things that all they do is churn out. Yeah, that's all they do. They just simply are hardware designed for doing a SHA algorithm, which means that basically now everybody has to move to a different hashing function. Because anyway, what are collisions in hash tables? So they occur because there's not enough space, and we can handle them with two methods: open addressing and chaining. Open addressing means if I get a collision, I'm going to put this key in the next available space. And we can put next in big quotation marks because next is defined by different things in open addressing.
It seems unsafe.
It works. That's what
I'm thinking nefarious. It's not necessarily nefarious, right? It could be like,
no.
it just happens.
And then chaining is the other way, which simply says that each we don't store one, each index in the array, rather than storing one item, is instead a linked list. And if we have multiple items there, we just simply add it to the end of that linked list. And so to find an item, all we do is just simply go to the proper linked list, iterate through it. All right. So what is the worst case runtime for insertion and deletion algorithms in binary search tree and why? Worst case for worst. So what's the average case? Not n-log n. Log n is the average case. Log n is the average case for adding an item to and deleting an item from a binary search tree. But what's the worst case? Notice that's that's a binary search tree as opposed to a balanced binary search tree. So if it's unbalanced, what's our worst case scenario?
Has to go through the entire tree.
Yeah, n.
Yeah.
Where basically, our worst case is that our tree looks like this. Is where our tree looks something like this. And you know what, we'll put an extra turn in here just because. Something like this. But basically where each, and then maybe, so we should probably do stuff like this as well. This is a highly unbalanced tree. Every single choice you make simply only knocks off one node from the entire search space, right? Going this way, we only lost one node. Going this way, right? We aren't cutting off an entire branch, we're cutting off a twig. Okay. Last question, which is this one, which is some stupid categorization question I made up. So here, right, this one was basically here, given an array of integers, categorizes them into numbers divisible by 2, 3, and 5. So here's our input, 1, 2, 3, 4, 5, 6, 7, 15. 2 have the items 2, 4, and 6 because those were the only items in here that are divisible by 2. 3, 3 had 3, 6, and 15 because those were all items that were divisible by 3. 5 had 5 and 15 because those were divisible by 5. Notice that an item like 15 appears in 2 lists. That's perfectly fine. Because I say a number can occur in multiple categories and none. So I'll just do this, and then we'll be done. Also, I should point out that I've been doing the practice questions as well, right? The ones that don't count, as well as explaining stuff, and going on random asides for this exam. And I'm still coming in, and if I finish this question by 1:50 when this class gets out, you're still going to have an extra half an hour after that to finish the exam. So it's plenty of time, is all I'm trying to say. It is tomorrow. And again, I'm not saying you shouldn't study, but to reduce your stress, right? The scores on this exam are generally high. So just I want you to come. You always come into these things better if you're not stressed about it. So, let's go ahead and create a map, integer to list of integers, and this one's going to be weird because unlike other things, we know what the categories are in advance. So. Categories equals new hash map. We know what the categories are in advance, so we can just put them in. Categories.put a list for all the numbers divisible by 2. New array list. Copy paste.
Because it's returning.
Because.
I thought you were just like, I think it's in line. No, never mind.
And then return categories. So, right, we've already populated our. So now all we have to do is actually iterate through the array. We don't have to check, hey, have we seen a number divisible by 2 yet? Because we've got an empty list for each of those. So for int I or int x in array, if x mod 2 equals 0, if the number is divisible by 2, categories dot get the 2 list and add x to it. And then just do it for the other ones. No if else's, by the way, because it can go into multiple categories. Insert, which actually is useful sometimes. 5.
Because then it falls through and does them all at the same time instead of like reevaluating.
Yeah, 5. So if it's divisible by 3, put it in the 3 list. If it's divisible by 5, put it in the 5 list. That's all that it is to it. All right, in the 5 minutes we have left, any questions?
Fine. Oh, sorry.
Behind verse, yes.
So for the is full function, the first if was if tree is full. So are we just defining like a null tree to be full? Like is that arbitrary?
Yeah, that was fairly arbitrary. I was going like, hey, if it doesn't have any nodes, I guess it's full because all the nodes have no or two children.
Probably something. There's probably something.
Scroll back down. All right, can you just keep the volume down for a second? I want to. Yes.
For 22, you said it's big O and
Sorry.
for big O for 22, you said big O and get the irreducible tree.
Oh yeah. I forgot the big O notation. Right. Which is something that happens on the exam sometimes, right? So, for 22. Yeah, it's big O.
Big O.
Yeah, this is big O-N. This is O of N. Right? It's linear time. By the way, the amount of time the is full so the amount of time 16 and 17 took, those are both O of N algorithms because you have to check every node in the tree. Right, if you do something that resembles pre-order and post-order, or just simply hitting everything in the tree, then it's going to be O of N. Yes?
For like 21, when you talked about chaining for collisions, how do you know? So in that sense, you have like say 2 hash codes that point to the same list or the same list.
You have two keys. You have two key value pairs that are in the same linked list.
Yeah. How do you so you might say you have 2 keys that point to that.
Yeah.
So how do you know which one you want? How do you know which one you want when you give us
So what you have to do is configure it in your linked list.
If it'll sit around, what do you want me to play? The government just stays up and is all
Basically,
you want
suppose you have apple and banana.
use your elliptical curve, DC how much 25, 5, 8.
And they go to the same index. And those last three you can start with apple first. What he's got is apple, banana, whatever. Yeah, and so you just simply search for banana. Banana gets passed to this thing. There's a list there. Get right through it. Like banana. Yeah, if you remember from what I was doing in the last video, I was creating something called an entry.
But you don't get to choose the happy.
Yes, that was hopefully
Yeah,
because, and so a lot of examples in the drawing stuff, I just assume we're just storing
not for passing and improving.
Yeah.
So is it like just like everything is a string, like every input is a string,
It's big, yeah. It's essentially big O of N, because so this one 22 is big O of N because in a tree, because in a balanced binary tree, what you do is you go left or right, and when you go left or right, you're essentially cutting out the entire left side of the tree or the entire right side of the tree. So you're cutting out half the nodes you have to search. But in an unbalanced tree, you're cutting out much, much less. You're maybe cutting out maybe 1 or 2 nodes at a time.
And that's what we are.
And so in a sense, you have to go through the entire node.
Okay.
Sorry, the entire tree.
Okay. All right. Thank you.
Yes.
I just had a quick question. Do you have a recommendation of any of the coding problems we can look at? Like if we're comfortable with all of like up until Huffman coding, or Huffman problem?